This is the screencast for section 4.6, example 3. In example 3, we are going to approach proving that this function is periodic, similar to how we have done the previous example. We're going to use the fact that the sine curve has a period of 2 pi in our proof. So we'll start out with f of x equals the sine cubed of x. Now I'm going to try and plug in f of that same x value just 2 pi later and see what happens to my final values. Now, I believe your book writes this differently, so I'm going to choose to do that as well. If I change the cube to the outside, it's easier to see that we are dealing with, in fact, just the sine of x plus 2 pi, which, because sine is periodic, has the same value as the sine of x. So I do in fact end up with the same y value as the original function when I plug in that same x value 2 pi later. So it is periodic. The period, after seeing from my graph, is 2 pi. The domain of this function is all real numbers, which makes sense. Sine, the domain is all real numbers, and all we're doing is cubing those values. There's nothing you can't cube, so you'll be able to plug in any number you want. The range goes from -1 to +1. And the reason I know that is because the old range of sine was -1 to +1, and -1 cubed is -1, and 1 cubed is +1. Now, to plug in some values, some x values, and show exactly how this function is created, I'm going to use the quadrantal angles from 0 to 2 pi. So f of 0, the sine cubed of 0, well, sine of 0 is 0, 0 cubed is 0, 0, 0 is a point on the curve. The sine cubed of pi over 2, well, the sine of pi over 2 is 1, 1 cubed is still 1, the sine cubed of pi is, well, the sine of pi is 0, 0 cubed is 0, so pi comes 0 is another point. Oop, I haven't been marking those. Here we go. The sine cubed of 3 pi over 2, well, the sine of 3 pi over 2 is -1, and -1 cubed is still -1, so 3 pi over 2, -1. And now sine cubed of 2 pi, the sine of 2 pi is 0, 0 cubed, 0. So now, the only difference that you can visually see is the concavity. We change from concave up to concave down, concave up to concave down. There's a little bit of wavering in here, very similar to a cubic function, the function x cubed. You can explore those other values in there on your own, for example, the sine of pi over 3 cubed, the sine of pi over 6 cubed, etc. Alright, the now try problem for example 3 is number 13. Number 13, the directions just say state the domain and range of the function and sketch the graph showing 4 periods. Well, the domain is going to be all real numbers again because I'm squaring the cosine function and there's nothing I can't square, and I already know that the domain of cosine is all real numbers. So just squaring all of those real numbers isn't going to eliminate any that can't be put in to the function. The range, however, is going to change. I know that cosine by itself fluctuates between -1 and 1 for the range. The minimum is -1, the maximum is +1. Now that I'm squaring everything, all the negatives are going to become positive, so my range is going to have a minimum of 0 and a maximum of 1, including both of those numbers. And I'll demonstrate that by plugging in some key values. The other thing I want to mention first, though, is I am going to use the 0, pi over 4, pi over 2, 3 pi over 4, and pi, because a period of the cosine function now is only pi. You can see that graphically, and it also makes sense because now that we are squaring the cosine values, the negative values are not going to occur. So instead of this function dipping below the x-axis and coming back up, it's just going to keep repeating itself over and over again every pi. Now, f of 0 will be the cosine squared of 0. Cosine of 0 is 1, 1 squared is 1. The cosine squared of pi over 4, that's square root 2 over 2, squared is going to be 2/4 or 1/2. Pi over 2, so the cosine squared of pi over 2, cosine of pi over 2 is 0, 0 squared is 0. 3 pi over 4, the cosine squared of 3 pi over 4. 3 pi over 4, see, quadrant 2, so that's negative square root 2 over 2, but squared will become positive 1/2 again. The cosine of pi is going to be negative 1, but then squared is going to be positive 1. So I have 0, 1, pi over 4, 1/2, pi over 2, 0, 3 pi over 4, 1/2, and pi, 1 as the 5 points in this period of the graph.